Cloud Computing and Supercomputing. There is a spectrum of philosophies on how to build large-scale computing systems. At one end of the scale is the field of high-performance computing (HPC). Supercomputers with thousands of CPUs are typically used for computationally intensive scientific computing tasks, such as weather forecasting or molecular dynamics simulating the movement of atoms and molecules. At the other extreme is cloud computing, which is not very well defined, but is often associated with multi-tenant data centers. Commodity computers connected with an IP network, often Ethernet, elastic/on-demand resource allocation, and metered billing. Traditional enterprise data centers lie somewhere between these extremes. With these philosophies come very different approaches to handling faults. In a supercomputer, a job typically checkpoints the state of its computation to durable storage from time to time. If one node fails, a common solution is to simply stop the entire cluster workload. After the faulty node is repaired, the computation is restarted from the last checkpoint. Thus, a supercomputer is more like a single-node computer than a distributed system. It deals with partial failure by letting it escalate into total failure. If any part of the system fails, just let everything crash like a kernel panic on a single machine. In this book we focus on systems for implementing internet services, which usually look very different from supercomputers. Many internet-related applications are online, in the sense that they need to be able to serve users with low latency at any time, making the service unavailable. For example, stopping the cluster for repair is not acceptable. In contrast, offline batch jobs like weather simulations can be stopped and restarted with fairly low impact. Supercomputers are typically built from specialized hardware, where each node is quite reliable, and nodes communicate through shared memory and remote direct memory access (RDMA). On the other hand, nodes and cloud services are built from commodity machines, which can provide equivalent performance at lower cost due to economies of scale, but also have higher failure rates. Large data center networks are often based on IP and Ethernet, arranged in closed topologies to provide high bisection bandwidth. Supercomputers often use specialized network topologies, such as multi-dimensional meshes and toruses, which yield better performance for HPC workloads with known communication patterns. The bigger a system gets, the more likely it is that one of its components is broken. Over time, broken things get fixed and new things break, but in a system with thousands of nodes, it is reasonable to assume that something is always broken. When the error handling strategy consists of simply giving up, a large system can end up spending a lot of its time recovering from faults rather than doing useful work. If the system can tolerate failed nodes and still keep working as a whole, that is a very useful feature for operations and maintenance. For example, you can perform a rolling upgrade. See Chapter 4, restarting one node at a time, while the service continues serving users without interruption. In cloud environments, if one virtual machine is not performing well, you can just kill it and request a new one, hoping that the new one will be faster. In a geographically distributed deployment, keeping data geographically close to your users to reduce access latency, communication most likely goes over the internet, which is slow and unreliable compared to local networks. Supercomputers generally assume that all of their nodes are close together. If we want to make distributed systems work, we must accept the possibility of partial failure and build fault tolerance mechanisms into the software. In other words, we need to build a reliable system from unreliable components. As discussed in reliability on page 6, there is no such thing as perfect reliability, so we'll need to understand the limits of what we can realistically promise. Even in smaller systems consisting of only a few nodes, it's important to think about partial failure. In a small system, it's quite likely that most of the components are working correctly most of the time. However, sooner or later, some part of the system will become faulty, and the software will have to somehow handle it. The fault handling must be part of the software design, and you as operator of the software need to know what behavior to expect from the software in the case of a fault. It would be unwise to assume that faults are rare and simply hope for the best. It is important to consider a wide range of possible faults, even fairly unlikely ones, and to artificially create such situations in your testing environment to see what happens. In distributed systems, suspicion, pessimism, and paranoia pay off. Building a reliable system from unreliable components. You may wonder whether this makes any sense intuitively. It may seem like a system can only be as reliable as its least reliable component, its weakest link. This is not the case. In fact, it is an old idea in computing to construct a more reliable system from a less reliable underlying base. For example, Error-correcting codes allow digital data to be transmitted accurately across a communication channel that occasionally gets some bits wrong, for example due to radio interference on a wireless network. IP, the Internet Protocol, is unreliable. It may drop, delay, duplicate, or reorder packets. TCP, the Transmission Control Protocol, provides a more reliable transport layer on top of IP. It ensures that missing packets are retransmitted, duplicates are eliminated, and packets are reassembled into the order in which they were sent. Although the system can be more reliable than its underlying parts, there is always a limit to how much more reliable it can be. For example, error-correcting codes can deal with a small number of single-bit errors, but if your signal is swamped by interference, there is a fundamental limit to how much data you can get through your communication channel. TCP can hide packet loss, duplication, and reordering from you, but it cannot magically remove delays in the network. Although the more reliable higher-level system is not perfect, it's still useful because it takes care of some of the tricky low-level faults, and so the remaining faults are usually easier to reason about and deal with. We will explore this matter further in the end-to-end argument on page 519. Unreliable networks. As discussed in the introduction to Part Roman 2, the distributed systems we focus on in this book are shared nothing systems, i.e. a bunch of machines connected by a network. The network is the only way those machines can communicate. We assume that each machine has its own memory and disk, and one machine cannot access another machine's memory or disk except by making requests to a service over the network. Shared nothing is not the only way of building systems, but it has become the dominant approach for building internet services, for several reasons. It's comparatively cheap because it requires no special hardware. It can make use of commoditized cloud computing services, and it can achieve high reliability through redundancy across multiple geographically distributed data centers. The Internet and most internal networks in data centers, often Ethernet or asynchronous packet networks. In this kind of network, one node can send a packet to another node, but the network gives no guarantees as to when it will arrive, or whether it will arrive at all. If you send a request and expect a response, many things could go wrong, some of which are illustrated in Figure 8-1. Your request may have been lost. Perhaps someone unplugged a network cable. Your request may be waiting in a queue and will be delivered later. Perhaps the network or the recipient is overloaded. The remote node may have failed. Perhaps it crashed or it was powered down. The remote node may have temporarily stopped responding. Perhaps it is experiencing a long garbage collection pause. See process pauses on page 295. But it will start responding again later. The remote node may have processed your request, but the response has been lost on the network. Perhaps a network switch has been misconfigured. The remote node may have processed your request, but the response has been delayed and will be delivered later. Perhaps the network or your own machine is overloaded. Figure 8-1. If you send a request and don't get a response, it's not possible to distinguish whether the request was lost, B, the remote node is down, or C, the response was lost. The sender can't even tell whether the packet was delivered. The only option is for the recipient to send a response message, which may in turn be lost or delayed. These issues are indistinguishable in an asynchronous network. The only information you have is that you haven't received a response yet. If you send a request to another node and don't receive a response, it is impossible to tell why. The usual way of handling this issue is a timeout. After some time you give up waiting and assume that the response is not going to arrive. However, when a timeout occurs, you still don't know whether the remote node got your request or not, and if the request is still queued somewhere, it may still be delivered to the recipient, even if the sender has given up on it. Network faults in practice. We have been building computer networks for decades. One might hope that by now we would have figured out how to make them reliable. However, it seems that we have not yet succeeded. There are some systematic studies, and plenty of anecdotal evidence, showing that network problems can be surprisingly common, even in controlled environments like a data center operated by one company. One study in a medium-sized data center found about 12 network faults per month, of which half disconnected a single machine, and half disconnected an entire rack. Another study measured the failure rates of components like top-of-rack switches, aggregation switches, and load balancers. It found that adding redundant networking gear doesn't reduce faults as much as you might hope, since it doesn't guard against human error, for example misconfigured switches, which is a major cause of outages. Public cloud services such as EC2 are notorious for having frequent transient network glitches, and well-managed private data center networks can be stabler environments. Nevertheless, nobody is immune from network problems. For example, a problem during a software upgrade for a switch could trigger a network topology reconfiguration, during which network packets could be delayed for more than a minute. Sharks might bite undersea cables and damage them. Other surprising faults include a network interface that sometimes drops all inbound packets, but sends outbound packets successfully. Just because a network link works in one direction doesn't guarantee it's also working in the opposite direction. When one part of the network is cut off from the rest due to a network fault, that is sometimes called a network partition or netsplit. In this book we'll generally stick with the more general term network fault, to avoid confusion with partitions shards of a storage system, as discussed in Chapter 6. Even if network faults are rare in your environment, the fact that faults can occur means that your software needs to be able to handle them. Whenever any communication happens over a network, it may fail. There is no way around it. If the error handling of network faults is not defined and tested, arbitrarily bad things could happen. For example, the cluster could become deadlocked and permanently unable to serve requests, even when the network recovers, or it could even delete all of your data. If software is put in an unanticipated situation, it may do arbitrary, unexpected things. Handling network faults doesn't necessarily mean tolerating them. If your network is normally fairly reliable, a valid approach may be to simply show an error message to users while your network is experiencing problems. However, you do need to know how your software reacts to network problems and ensure that the system can recover from them. It may make sense to deliberately trigger network problems and test the system's response. This is the idea behind Chaos Monkey. See reliability on page 6.